In this segment, I want to talk a little bit about capacitors and their connection to potential. So far, we've learned about capacitors as a way of creating a uniform electric field and as such a linearly varying potential. But capacitors are also used to store charge. This is one of their primary functions in a more complicated circuit. So we're going to talk a little bit more about that in this segment. This can be done in a number of different ways. A battery actually uses chemistry to separate charges. So it's actually a chemical reaction that happens inside your battery that causes a separation of charge and produces a voltage at the terminals. And depending on what kind of battery you have, a lithium-ion battery, a nickel metal battery, or there's different types of batteries, lead acid battery, that's what's in your car. Depending on exactly what type of battery you have, it's a different chemical reaction that's happening to separate the charge. But that's how the charges get separated. As the storm clouds move across the surface of the Earth, little water droplets pick up excess charge. And so charge gets separated, and actually you can build up an enormous potential between storm clouds and the ground, which eventually discharges in the form of a lightning strike. This is a Van de Graaff generator. If we were in the classroom, I would be able to demonstrate this for you, but perhaps you've seen pictures of this elsewhere. A Van de Graaff generator has a belt on it that carries charge from an outlet where you're plugged in and deposits it upon this globe at the top. And it turns out that a Van de Graaff generator can create an enormous potential, something like 100,000 volts in a typical Van de Graaff generator. And when this individual touches that voltage, it causes their hair to get charged up and all stand on end. So that's kind of fun. You might say, how can she do that safely? It turns out, we'll talk a little bit more about this in a couple chapters, it turns out that it is current that is potentially damaging to humans, and not potential. So it's not the 100,000 volts that might or might not injure this person. It is the current that is or is not flowing through them. Now, that's not something we've defined yet, but a current is a flow of charge. And it turns out that there is very, very little current flowing through this person. And so they can do this very safely. Another place that we've seen potential created is in a capacitor, right? And so a capacitor separates charge. We get one side charged up positively, one side charged up negatively, which creates that potential difference. Of course, with no separation of charge, we have no potential difference. Okay, typical electric potentials. Of course, you don't need to memorize these numbers. This is just to give you an idea of what the heck is a volt. You can measure the brain activity at your scalp. That's something like microvolts. It turns out that the action potential in our cells is about 70 millivolts, a little less than 100 millivolts. And so it turns out that it is a wave almost of potential moving along your nerve cells that is the way that your brain tells your muscle to do something. Okay, that's kind of cool. A battery, I showed some at the beginning of this chapter, 1.5 volt batteries. Of course, 9 volt batteries are very common. The battery in your vehicle is probably 12 volts. Household electricity is 120 volts, typically 100 to 120 volts. Your dryer probably runs on 240 volts. That's AC voltage, alternating current. That's something we'll talk about in a little while. Static electricity, you can get kilovolts. Even it's probably kilovolts that develop between your finger and the doorknob before they discharge. So that's kind of interesting. Transmission lines, again, we'll talk a little bit more about this in a couple chapters. When they're bringing the electricity from the power plant to your city, those, what they call high-tension power lines, are probably running at something like 500,000 to 1 million volts. All right, so at any rate, we can have voltages, potentials, from very, very tiny potentials all the way to millions of volts. Well, maybe I won't quite say our daily lives, but around us, certainly. So in order to charge a capacitor, let's talk about how we charge a capacitor. We're moving charges. Remember, in general, it's the electrons that move because the protons are bound within the nucleus. In general, we're moving electrons. And so how do we do that? Well, we need to take a few electrons off of a positive plate and deposit them on the negative plate. That leaves a residual positive charge over here and a negative charge over here. If I move a little bit more charge, then I get a greater E field and a greater potential difference. How do we move that charge? Well, we'll talk about that one a little bit more in the next chapter and the one after that, but that's the basic idea. How much charge can we develop if we hook it up to a battery or something? Well, it depends on the capacitance of the capacitor and the voltage that I hook it up to. So the capacitance of the capacitor, that basically says, well, how much charge can this hold if I hook it up to a given battery? So again, Q here is our charge, C is what we call the capacitance, and this is the voltage. Why do we say, or the potential difference, I should say. It's V sub C because I'm saying that this is the potential difference across the capacitor. You know, we do have a special unit for capacitors. They're important enough that we do have a special unit. It is the farad, named after Mr. Farad, presumably, which is 1 coulomb per volt. It's this version of the unit, a coulomb per volt, is instructive because the capacitance says, okay, how much charge will this store for a given potential, right? So it really is charge per volt. So here I have one of these capacitors. So you can see that this is a 10 microfarad capacitor. You can see it's rated up to 250 volts. That doesn't mean it's always at 250 volts. That means that this capacitor will work for voltages less than 250 volts. It means that if I try and run 300 volts into this, that it's probably going to explode. That's fairly typical value there. You get all kinds of different values. This one is, I don't know, half a microfarad. A farad turns out to be a very large amount of capacitance. It turns out to store a whole lot of charge. This one right here, you can see, this guy is a 1 farad capacitor. I bought this just for demonstrations in class. But you can see it's only rated up to 5 volts. Right? That other one was rated up to 150 volts. You know, this one's rated up to 600 volts. But at any rate, that's what the capacitance is. It says how much charge per volt can a capacitor hold. Now, the capacitance is determined by the shape of the capacitor. We'll talk about that in just a second. So here we're going to hook this up to a battery. This capacitor up to the battery. This might be one way that we could charge up a capacitor. So it turns out that current is going to flow around here in a clockwise fashion. Positive charges would flow in a clockwise fashion. So positive charges would be delivered here. They would move off of here and into the battery. Now we know it's really electrons that move. So we can visualize this as positive charges moving clockwise or negative charges moving counterclockwise. So this is the basic idea of how we charge up a capacitor. This will continue until the voltage across the capacitor equals the voltage across the battery. So if I was using one of those 1.5 volt batteries to charge this up that I was showing the other day, then this would continue to happen until the voltage across the battery and the voltage across the capacitor were equal. In that case, it would be 1.5 volts. Then basically we would have the capacitor trying to push charge in one direction, we'd have the battery trying to push it in the other direction, and an equilibrium would be reached. Once we do that, we could remove the battery, and the capacitor will remain charged up. In this way, a capacitor can be used to store charge. So it can store charge. Because it's storing charge, it also stores energy. And as it does so, it creates a uniform electric field. So far, that's why we care about capacitors. Let's do a real quick numerical example. A 1.3 microfarad capacitor is connected to a 1.5 volt battery. What is the charge on the capacitor? This is a fairly straightforward example. We can kind of just charge through it. We're going to use our equation here, Q equals C times V. in this case, C is the capacitance of our capacitor, which is 1.3 microfarads, or 1.3 times 10 to the negative 6th farads. We hooked it up to a 1.5 volt battery. Run our calculator and we get 1.95 times 10 to the negative 6th coulombs. So not a terribly challenging problem here, but this is the basic function of a capacitor here, is to store charge. We're storing charge. How much charge do we store? Well, for a given capacitor, it depends on the battery I hooked up to, right? So for example, I showed you this just a second ago. This is a 1 farad capacitor. It's 1 farad capacitor whether it's not hooked up to a battery, I hook it up to a 1 volt battery or a 5 volt battery. It doesn't matter. The capacitance is still the same. Uncharged, charged, connected to a battery, not connected to a battery. It doesn't matter. The capacitance is defined by, honestly, the geometry of the metal plates and whatever else is in here. It's not defined by what the circuit is that I hook it up into, or whatever elements I hook it up with. So again, capacitance times potential equals charge. Notice here, if I doubled the voltage, I would double the charge. Half the voltage, half the charge. Capacitors are everywhere. They're just everywhere. Modern electronic devices might contain many thousands of capacitors. Your cell phone, it probably holds, thousands, hundreds of thousands of capacitors. Here's a zoom in of what a capacitor might look like in an actual integrated circuit, which is just a tiny, tiny little electronic device, which might be in your cell phone or your calculator or your computer or any electronic device really is going to have some capacitors in it. So here we see, this is a zoom in, and each long structure is one capacitor. Whatever this is sitting in must be a conducting medium. That is the positive electrode. The negative electrode is this thing that points down into here, and it's wrapped around with an insulator. So again, this is just an example of what an actual capacitor might look like. We could store charge and energy in a capacitor, but you could also use it to store memory, right? For example, the original computer memory was all magnetic. So a magnetic field pointed this way might be a 1, and pointed this way might be a 0. Here we could say, well, if my capacitor is charged up, that's a 1. If it's uncharged, it's a 0. Obviously there's some details to work out, but that's the fundamental idea of solid-state memory. Like your USB memory stick. That's the basic idea of it. Instead of recording memory as magnetic fields, we're recording it as some sort of electronic storage, and a capacitor is one efficient way to do that. So, among the various things that I like to do with my life is build guitar amps. This is a guitar amp. Here's the insides of it that I built. This is based on a classic 60s Fender design. The point is, there's a whole bunch of capacitors involved in any electronic circuit, including guitar amps, which is certainly one of my favorite circuits to talk about. All these little orange guys, those are all capacitors. These are capacitors, very tiny ones, small. Those are nanofarad, picofarad capacitors. Capacitor, all these orange things are capacitors. These big guys right here are huge capacitors. Those are on the front end. Those store charge and smooth out the power supply. So they make it a little bit quieter. Anyway, capacitors in here filling different roles, but man, there's just a bunch of them in here. So like I said, the capacitance of a capacitor is really defined by the geometry of the capacitor. And so here's our equation for that. The capacitance, it depends on what? The area of the plates and the separation between them. Remember that we're talking about, in this class, a parallel plate capacitor, which is two conductors that are sheets that are parallel to each other. That's what we're talking about. So what is A in this equation? It is the area of one of those sheets. D is the distance between them. And epsilon naught is just that constant, 8.85 times 10 to the negative 12th meters squared per Newton Coulomb squared. Again, a capacitor stores energy. How much energy? Well, it depends on the voltage across the capacitor. Of course, the voltage across the capacitor is proportional to the charge, so we can write the energy stored as a function of the charge or as the voltage. We're using U here because it's storing potential energy. It's storing electrical potential energy. It is the positions of the charges on the different plates that give the capacitor its energy. Here's a quick example. Here we've got a capacitor. It has a charge Q. The plates are pulled apart so that the distance between them is larger. And to be clear here, I've charged the plates up, I've removed the battery, and now I'm going to pull these apart. Now, I'm doing this with some insulated gloves or something, so I'm not interacting with them. I'm not pulling charge on or off or anything like that. The only interaction here is me pulling the plates apart, right, with my insulated gloves. What will happen? Will the charge increase and delta V decrease? Will the charge decrease and delta V increase? Will both the charge and delta V increase? Or will both the charge and delta V decrease? Or will the charge remain constant and delta V increase? Why don't you think about it for a moment, and I'll see you on the other side. Okay, so for this one, what we want to do is we want to look at this equation, and we want to see what remains the same and what changes, and how that might affect the other things. Okay, so first let's look at the capacitance. If I pull the plates apart, what happens to the capacitance? Well, epsilon naught is a constant. A hasn't changed. What has changed is D. If D goes up, the capacitance goes down. So we see here that the capacitance is going to decrease here. Now, how will that affect the voltage across the capacitor or the charge on the capacitor? Well, remember about the charge. Remember our charge model. Charge is carried on a physical thing, right? Charge is carried on subatomic particles. An electron carries a negative charge, and that's what moves, right? So if we're going to get charge on or off of these plates, electrons need to move on or off of these plates. Now, the air is an insulator. The air is not a conductor. So those electrons can't just travel through the air. If the air was a conductor, then capacitors would just not work at all, right? So electrons can't just move from one plate to the other. It's not hooked up to a battery. I'm using my insulated gloves to separate them. There is no way for Q to change. Therefore, it stays the same. Okay, so Q is the same. If C decreases, in order to keep Q the same, the potential must increase. So, which of these answers says that charge stays the same and the potential increases? E. It's a little bit tricky. Again, we look at this equation, we see what stays the same and what changes. So here now we have a capacitor attached to the battery. So I've charged it up, and now, well connected to the battery, I am going to pull the plates apart. Now what happens? Will the charge increase and delta V remain constant? Will the charge decrease and delta V remain constant? Will both the charge and delta V increase? Will both the charge and delta V decrease? Or will the charge remain constant while delta V increases? Why don't you think about it, and I'll see you on the other side. Once again, I am increasing D. Therefore, the capacitance is, once again, going down. So that is the same. However, now, if we look at this, a battery is a source of constant potential. Charge can flow in or out of a battery, but A battery is a source of constant potential. If you look on your battery and it says 1.5 volts, as a AA or a AAA battery does, that means it puts out 1.5 volts basically in all conditions. Now, real batteries, that can vary a little bit, but in this class, we're concerned with ideal batteries where it doesn't vary at all. So, if it's continuing to hook up to the battery, then V stays the same. We can see here that if V is the same, C decreases, the charge must decrease. Charge must be flowing off of the capacitor and into the battery. And indeed, the charge decreases and delta V remains constant. It's a little bit tricky. So guitar amps is a great place to find a capacitor. It turns out that there's an enormous capacitor in a defibrillator device. When your heart beats, it's because there is a wave of action potential that sweeps across your heart and back across. And it makes all of the cells in your heart all act together. Or not exactly at the same time, because we know that the two halves beat at different times, but like they're supposed to, let's say that, right? Working together as a team in the way that they're supposed to, all of the cells in your heart. And it turns out that this action potential, it's just a potential. It really is a potential. It's about 70 millivolts. And when the neighboring cell reaches that 70 millivolts, it tells the next cell, hey, it's your turn, go for it, buddy, and then on down the line. And it creates this rhythmic system where all of your cells are working together. Now, unfortunately, sometimes your heart can enter what's called a state of fibrillation, where those cells are not working together. They're triggering at different times. We don't get this wave of action potential sweeping across our heart, but rather some random triggering and release of that action potential. One way to reset it is to produce a huge voltage across your chest. Bam! That syncs everything up and stops that fibrillation, we hope. Hence the name defibrillator. The way that works is with a massive, massive capacitor that can pump a ton of energy into a person all at once. A defibrillator has a large capacitor. It can store up to 360 joules of energy and release it in a very, very short amount of time. So again, just another practical application of a capacitor. We'll see more as we move through the next few chapters and talk about how to apply this electrical world in sort of a practical way. So the next couple chapters, we're going to start talking about charge in motion or current, and the devices, the electronic devices that fill our world, all have to do with charges in motion.